I'm a mechanical engineer.
Right.
For me, basically, friction is thy enemy.
Okay.
Right? We actually treat it in that way.
Right.
Friction is bad for us. Friction is bad for the systems and the designs that we make.
Not only for you, but also general people in different ways.
There is no perfectly flat surface. Right. So every surface, if you look at it from the micro angle, will have ups and downs. Right. Undulations.
Is it possible to create a system of moving parts where friction can be negligible, close to zero, not zero, exact zero, but the ancient cavemen,
absolutely,
when they were discovered fire, they were playing with friction, right?
Exactly, they were
they were the inventors of tribology.
Absolutely. Probably yes.
Yeah. And there's also a painting in ancient Egypt. I had seen it long back, where in the painting the slaves are moving the stone to the pyramid, and somebody is pouring the oil to the rope.
You see, exactly. Now you're talking about a fluid film which is in micrometers, very thin. But even inside that, there is friction between fluid layers.
Interesting. Now, pretty curious about grease's component. I never thought, what is grease made of? Welcome back to QAT Podcast. Topic for today's conversation is friction. You heard it right, friction. And the most interesting part of it, one of the most interesting part of friction is friction has its own field of study, and it's called tribology. And I was intrigued when I heard that 4 years ago, that friction has its own field of study. Today, we have a chance to get deeper into tribology. And the guest for today's podcast is Dr. Binu KG. Welcome to the podcast, sir.
Thank you, Clinton. It's a pleasure to be here today, and this format is new to me, so I'm excited. Let's see where this goes.
Right.
Yeah.
So Dr. Binu is the professor of mechanical engineering at St. Joseph Engineering College, Mangalore, and his specialization is tribology.
That's correct.
And I heard you did your PhD in lubricants, nanolubrication.
Nano lubricants is my field of research.
Okay.
Yes, yeah.
So why so much fascination on lubrication?
No, if I take a step back, while I was doing my master's, tribology was an important subject in my MTech course. MTech course was on maintenance engineering, right? So tribology as a field is not, I should say, not spoken about much. It's this backstage.
Right.
We have heroes on the front end, automotive engineering, automation, robotics. Right. These are the areas which people speak about. Stand out. Right. But tribology as a field is quite paramount. It is very important. All these other fields do well because there is sufficient progress in the field of tribology that has happened over the year.
It's like a Batman of engineering.
Exactly. And the reason why I was drawn to this field of study is because there is this good mixture of theory and experimental work, right? Which is very unique, right? Because right from first principles, tribology has got very strong theoretical background.
Right.
The mathematical models.
Physics.
Exactly. The mathematical model that governs the lubrication phenomenon is so well defined and so solidly mathematically modeled. Right. So there is immense scope to research in that field. Right. So there is a lot of good mathematics at play. Similarly, there is plenty of scope for experimental work as well. Right. So this combination was very appealing.
Right.
To be stuck in only experimental work was not that appealing to me. So that attracted me to this field.
Seeing mathematics and physics and seeing its theory play out in the experimental
world, to try something out mathematically and then validate it. It gives an immense sense of satisfaction. And I'm not sure if you know it, but there is close to more than 25% of the power that we generate and utilize is going waste purely because of friction. Right. So from a sustainability angle, it is very important. Okay. Tribology plays a big role in conserving energy, reducing loss of energy, right? So
it can contribute GDP of a country, we can say.
immensely. You know, a good portion of worldwide GDP, I'm sure, is going waste because of what happens to friction. But then, you know, friction is unavoidable.
Right. And let's imagine the world without friction.
Yeah, that will be a static world. Right. Everything is still.
Can we have the podcast just like this without friction?
Absolutely no. Because you know, we live in a dynamic world, right? The world is so dynamic, and unless there is relative motion happening, that would be a very sad world. Right. So friction is you can't reduce it down to zero. Right, but the effort is always to minimize it. I'm a mechanical engineer. For me, basically, friction is thy enemy.
Okay.
Right, we actually treat it in that way. Right. Friction is bad for us. Friction is bad for the systems and the designs that we make.
Not only for you, but also general people in different ways.
Absolutely. You know, while PhD, we used to talk among our friends that there is a philosophical note on tribology, right? Because just like how there is friction in life, right? Friction in machines, there is friction in life as well, right? So tribology is similar to the life care and taking care of your health. So those, how crucial it is for us as human beings, right? The same holds good for our machines as well, right? So that love for machines and the need to keep them durable, function for a longer period of time, that's the job of a tribologist, right? Yeah.
To give a long shelf life for machines.
Absolutely.
Nice.
It's very critical.
So let's get deeper. So we'll start from the basics.
Right.
Basics and then friction.
Sure.
Then we will evolve into tribology. We will see how complex is the field, what are the possibilities, what are the applications that we will get into in a while.
Right.
This is my first engineering podcast. I've never done engineering thing, and my background is life sciences, biological, but I'm quite curious.
Sure.
So let's start from friction.
Right.
So how would you define friction in a definition way?
Right.
And where else, apart from moving parts, what are the other interesting places or unusual places where we see friction's role in friction's role or friction in play that we are not really aware of?
Exactly.
Okay.
Yeah. So let me begin by saying that, you know, as I said before, relative motion is crucial to our existence, right? Everything that we, as mechanical engineers, everything we design and everything that moves, there will be two surfaces that will be in relative motion, right? That is, there will be under force. These two surfaces are pressed against each other and they move, right? And they move opposite to the directions are in the opposite way, right?
Is it always or
usually, right? Usually, most of the time, right? And that surface contact, right, induces friction, right? Because there is two surfaces. See, any surface that you might view it at a micro level will have like asperities. There is no perfectly flat surface. Right. So every surface, if you look at it from the micro angle, will have ups and downs. Right. Undulations. And those undulations, when they rub together, right, generates heat. Right, which a good portion of the prime mover energy that you provide to move the surfaces, that energy gets lost as heat, right? And this happens because of friction. Now, since you are from a life science background, the joints that we have, right? Say, for example, if I will take the case of a knee, right? So there is the bones move relative when you are actually walking, right? And there is a synovial fluid there which acts as a lubricant, right? So friction is there between that.
And when it dries up, it makes a noise as well, right?
Exactly. And that's lead to arthritis, if I'm right. Okay. So friction is fundamental in physics. Wherever there is surfaces in contact undergoing relative motion, friction is unavoidable. Okay, it's fundamental.
So fundamentally they are caused by the the topological differences, undulations in the surface.
Absolutely, asperities in the surfaces.
So friction is very atomic. It's not macroscopic phenomenon. It happens in the microscopic way,
absolutely.
but it is observed in the macroscopic, is it?
Absolutely. See, when we study friction, we study it from both the micro and the macro level. Right now, when you're looking at it from a macro level, you're not worried about the undulations, the asperities. Your systemic view is in the macro scale, right? But to say, for example, when you're designing precision instruments, right now, precision instruments needs to be studied at a much smaller scale. Because the even a minute 1 degree angle, right, will actually induce a heavy loss, right? So tribology is a field where you study systems at both micro and macro level.
Interesting.
Right? Say, for example, there is something known as, in my field, nano tribology, right? In which friction wear is studied at the nanoscale, right? Where the physics is not the same. Classical mechanics
doesn't play
a role, right?
So what does it play? Quantum?
It does. Okay, you will have quantum effects in play. Then you will also have to think in terms of non-Newtonian. If you are like talking about fluid motion, right? Then Newtonian fluid mechanics won't apply. Right, so there is non-linear fluid flow that you have to study, right? So yes, it's quite interesting, both at the micro level and at the macro level.
Nice. So any other unusual places you mentioned about the knee joint?
Everywhere. The other, see, what I primarily deal. Let me just give you an example of. Computer systems.
Okay.
Right now, processors are extremely powerful these days. Right. So even CPUs also, there is a lot of friction that takes place there. Between say, for example, in older systems, right, there are a lot of electronic systems which actually, say, for example, let's actually talk about the case of a fan. Okay. Right, the processor needs to be kept at a minimum temperature, right? Therefore, you have fans there, right? And the spindle of that fan runs at an RPM of 1500, right? Where there is a lot of friction involved. So how do we keep that system working well? Right. So there are electronics also. There is a lot of applications these days.
When I hear about friction, there is I recall a sport which is called curling. Have you seen that? Like there are players sweeping the ice to control the direction of the stone and even the speed of stone to direct it to hit. Have you not aware of that game? Curling.
Curling. Okay, curling. Yeah. Okay. No, I have not heard much about it.
Yeah, I mean, where the players basically play with friction.
Okay.
And even geckos, when they move, they apply and play with the friction, right?
Sure. Yeah, see, there is a productive side to friction as well, right? Say, for example, grinding. Okay, grinding as a manufacturing process requires friction, right? So friction is not always bad.
Yeah.
Right. There is very productive use of friction as well. Right. Say but largely it is it's actually considered evil because of the influence it has on wear. Right. It is directly proportional to the wear that happens over a period of operation. Right. So machine degradation is a process that is largely due to friction. Right, so it becomes imminent that you follow good lubrication and make sure that we utilize the life of the machine to the maximum.
And you have to keep on changing the oil.
Exactly, lubricants play a crucial role. Right?
Last time I spoiled my bike, like without untimely using
Absolutely,
the
there will be
lubricant,
seizure.
like the engine got stuck.
Exactly, that's precisely. I mean, seizure is like imminent. The moment you have oil starvation in an automobile, seizure is like imminent. It will happen. It should happen, in fact.
Right.
So, yes.
Cost me a lot. Like
Definitely. So, my professors used to always like say that it is important that we link lubrication to the discipline with which we live, right? So
can you repeat?
so it's like, he used to always say that that there will be multiple points in our life where there will be friction. He used to take it to a philosophical notion, right, where he used to say that the good food habits that you have, the exercise that you do, all these are the lubricants that keeps your body running smoothly.
Is it possible to create a like system of moving parts where friction can be like negligible, like close to zero, not zero, exact zero, but very close to zero? Down the line, I don't know whether if there is a system like that now.
There is research happening on certain areas where they are trying to design out friction, right? In the sense, there is a law that holds on the materials that you actually choose, right? So, one way of minimizing friction is to have sacrificial layers in between. Right?
What do you mean by that?
Say that you've got two steel structures, right? Now, steel structures are by nature hard, right? So, when they are in contact and they move, friction is bound to happen. But what if I have a softer material in between, right, which will shear off easily, right? And shearing of those sacrificial layer will not affect the performance, right? And at the same time, it will bring down friction as well, right? Say, for example, let's take the case of a journal bearing. A journal bearing is something which will support a rotary shaft, right? When we have to transmit power from the engine onto the wheels, you need shafts, right? And these shafts will have high RPMs and they need to be supported, right? And journal bearing is a means of supporting these shafts, right? And what happens is you have a shaft, and in between the shaft surface and the bearing surface, you will have the lubricant. Okay. So that is how the rotary system works. Now, this bearing, the inner lining of that bearing can be Babbitt lined. Now, Babbitt is a material which has got very low shear strength, right? So the moment there is shear, it will shear off in like small amount, right? And once that Babbitt layer is completely worn out, you can reinstall it.
Okay.
So you are avoiding contact of two hard substances by providing a much lower shear substance in between. That is one way in which you can bring down friction, right? But to completely remove friction, don't think it's possible.
Like getting deeper into atomic level, and you play with the surfaces atomically.
Exactly.
You align the
absolutely
the what do you call the incubarances?
Okay.
Undulances. Perfectly or something.
No, if the undulances or the attributes align, they get stuck.
If it's not aligned, misaligned.
Correct. It should be.
If it's in different direction.
Yeah, correct. It should be. If it is, you can actually promote. See, one of the aspects of my research while I made use of nanolubricants is, it is a lubricant in which I add inorganic material as lubricant additives. Right now, these additives are at the nanoscale, typically 100 nanometers. Right?
What nanoparticles?
I worked on something called as TiO2, titanium dioxide, right? And there are plenty of additives out there in the market which has been worked upon, right? And some of the lubricants that are available in the market, they do have nanoparticles as lubricant additives. But the issue is something else. I will speak about that. But when you have nanoparticle additives present in between the two shearing or the two surfaces undergoing relative motion, this undulations that we spoke about, all right, these particles being strong, they actually tend to break them and even it off. Right?
So they will fill the space where there is the valley kind of thing.
Exactly. And some of the peaks, it will break it off. Right? That way it is a mending effect. Okay, mending effect on the surface, which will then bring down friction.
How significantly?
It does. In my research, the use of nanolubricants has found to bring down friction by 15 to 20%.
Not bad.
Right. It is. Yeah. I mean, that's the reason why there is plenty of interest now. Right. The amount of research and amount of publications that is happening in the field of nano lubricants is quite high. So there is definitely benefits. But the issue is when you are adding nanoparticles to a fluid, it affects the shelf life of the lubricants.
How come?
In the sense, these nanoparticles, unless they remain in a suspended state, right, it doesn't contribute, right? But when you are keeping lubricant aside, right, in its bottle and can or something like that, over a period, these nanoparticles, which have got very high surface energy, right? When you go to nanoscales, individual particles have got very high surface energy. Their surface to volume ratio is very high.
That means, do they sink down or do they?
They do. They actually tend to agglomerate, and the moment they agglomerate, they will sediment.
Oh, okay.
Right, and once sedimentation happens, then it's of no use.
So there has to be constant agitation in the.
Absolutely. So you cannot have nano lubricants lying on your shelf for long. Right now, this sedimentation problem, which we call as nano fluid stability. Right now, this nano fluid stability is a field of study which is yet to be resolved. Right now, this problem of stability is still there. There are many ways in which we can improve it, say by effective use of surfactants. Now, in my research, I tried out many things, and there was one sample that stayed stable for 86 days, okay, which for me was a big deal. I mean, this was 10 years back, right? So there are means in which you can extend the suspended stability, but then not for long, not for months, right? So that is another drawback. But it is proven that without any doubt that the presence of nanoparticle additives in lubricants will bring down friction.
Nice.
That's actually a proven thing.
There's growing interest.
Absolutely.
I want to touch tribology. Yeah. So, what is tribology?
Right.
Like, if you were to explain this to a layman terms.
Yeah.
How would you define tribology?
Okay.
And why would people should? How does tribology play a role in people's life, everyday life, without them realizing it?
Yeah. Tribology as a word, it has its root in this Greek word called tribos. Tribos means to rub, right? So this field of study is not new. Tribology, even though the term is not very popular among men of science, it is not a new science as such. It's actually very old.
Like the ancient cavemen,
absolutely,
like when they were discovered fire, they were playing with friction, right?
Exactly, they were
they were the inventors of tribology.
Absolutely. Probably yes. Right from when people started moving things, okay, say for example the chariot wheels, right, that's when they actually felt that the rotary motion gets affected by friction. Right. So if you want smooth motion, you need to use substances which will slip. Right. So people started using animal fat, oils. Right. So many of these items were used as lubricants.
Right. And there's also a painting in ancient Egypt. I mean, I had seen it long back where in the painting, the slaves are moving the stone for the pyramid, and somebody is pouring the oil to the rope.
You see, yeah, exactly. So it's not new science, but then over the years, the need for efficient lubricants became very high, because see, now we speak about powerful machines. See, why is an F1 vehicle possible? Okay, we have prime movers that can power that, right? But on a practical level, unless you have the tribological knowledge to prevent friction in such high-powered machines, they will not work, right? So growth in automotive sector, transportation, manufacturing, all this is made possible because of the knowledge that we were able to build up in the field of eliminating friction and wear. Right, so tribology as a field of study has grown along with every other field. Right, so there is three things that tribology as a field looks into. Okay, primarily, as you said, friction. Okay, friction is one important component of this field of study. Second is a result of friction, which is wear. Right, where you actually define it as loss of material under frictional force, right? And the third aspect is lubrication. So friction, wear, and lubrication are three important angles, three important components of tribology as a field of study.
So you can say it is intersection of physics, mechanical engineering, and material science.
A lot more than that, I should say. I will say that mechanical engineering is fundamental because it deals with the forces involved.
Wear and tear.
Correct. Yeah.
The friction from physics.
Exactly.
And lubrication from material science.
Absolutely.
Is there any other components or other field of study?
I would say that physics is important, right? Material science is important, as you said, because tribological property is highly subjective to the material that we use, right? So that way, material science makes sense. There is a lot of chemistry involved in the process, right? So there will be a lot of because in a lubricant, right? In a lubricant, there are plenty of chemicals that we add, right, to actually promote the creation of a thin film between the two interacting surfaces, right? So chemistry plays an important role, right? So physics, chemistry, mechanical engineering, as you said, material science for sure, and then the way you have modeled the system, mathematics plays a key role, right? Therefore, it is an intersection of multiple fields. And nanotechnology, there is an entire field known as tribology that I actually spoke about, which is a new field of study, right? So it is a mixture of a lot of fields of studies. Right?
Cross-field collaboration.
Absolutely. It's multi-disciplinary in its true sense.
Right.
Yeah.
So you said there are three things. One is friction, one is wear, and one is lubrication. So what are the other complexities? Like, is there I want to understand how complicated is this field?
Correct.
Let's get into it. Like, where do you start from? Like, if you were to start tribology,
okay,
like learning tribology, like basic concepts.
Okay.
So where do you start from? Is there a loss of tribology or something?
Absolutely. See, as I said, the physics of lubrication or the physics of friction, lubrication, and wear is theoretically well defined. Okay. If you're starting from first principles, a good point to start will be the Navier-Stokes equation, because there is a lot of fluid flow involved. Okay. Now this lubrication mechanism is defined by something known as Reynold's equation. Right. So Reynold's equation, it's actually a big equation. There is actually multiple parts to it. It's a nonlinear equation, and this Reynold's equation will take into account all aspects of the lubrication process. right? So, I'm talking about hydrodynamic lubrication here. Now, let me, break it down a little bit for you that when you have two surfaces and a gap in between in which you have your lubricant, right? There are three things that can happen. One is the load that acts on these two surfaces are such that it will bring the surface in contact. Most of the asperities that we actually spoke about, the undulations, right? They will be in surface contact. No, even though you have lubricant film, there will still be some amount of solid surface to surface contact, right? And the resulting lubrication is what we term as boundary lubrication, right? Which is where you have maximum loss of energy. Friction is very high, right? Now, if there is sufficient speed and the load is less, you will have a case where the surfaces are completely removed and you have a thin lubricant film in between. There is no surface contact here. Okay, the two surfaces are completely separated and there is an oil layer in between, right? Now, such lubricant system is known as hydrodynamic lubrication. Right now, I study this. Okay, my field of interest in hydrodynamic lubrication, right, where there is total separation, but then there is friction even there. Right now, this is because the fluid film that gets formed in between, right? These fluid film works in multiple layers. And there is shear forces between every layer. Now, you're talking about a fluid film which is in micrometers, very thin. But even inside that, there is friction between fluid layers.
Interesting.
Get it, sir? And that friction is sufficient to bring about significant loss of energy, right? So, even if I use lubricant, friction is still there. Even if I avoid complete surface contact, friction is still there. Right? So how do I minimize that? That is when we thought of having nanoparticles there and see because the moment lubricant becomes hot, it will lose its lubricity. Right? Viscosity will go down.
Tribology.
Absolutely.
The higher the temperature, lesser the lubricity, is it?
Yeah, because with temperature, viscosity of the lubricant will go down. There is a negative relationship between viscosity and temperature.
Interesting.
Right? So, but then when you add these nanoparticles to it, they will arrest the fall in viscosity. Right, because of the physical presence of nanoparticles, right? So that is something that I thought of working on. Can we bring down the drop in viscosity even at high? Because when in a journal bearing, right, the lubricant temperatures can go up to 60, 70 degree Celsius, right? So can we still bring in sufficient viscosity to cause the presence of the lubricant film, which will bring down the friction, right? So that was the attempt, right? And we were quite successful in that. As I said, we were able to prove that presence of 0.05 percentage of percent weight of nanoparticles in an engine oil when operated in a journal bearing can bring down friction by 15 to 20%. Right, so that was one of the research finding that we had, right? So, but then issue is, as I said, nano lubricants, while it is very promising, its shelf life is an issue, right? So, coming out with a product, is like coming out with a marketable nano lubricant solution is yet to happen, right? Because of these issues with stability, and the economics is also not that viable, because even though there is tremendous progress in synthesizing nanostructures, right? Even now it is still expensive, right? So to add them as additives in your lubricant, right? The economics doesn't work out, right? So it's also something that is being worked upon.
Okay.
Yeah.
So any other equation or law to keep in mind? One you have mentioned some, like high temperature lubricity. There is a loss in lubricity.
Correct.
And anything in other interesting concepts in tribology, like interesting basic fundamental laws.
Yeah. So as I said, Reynolds equation is the governing equation, right? Now, which was developed in the maybe 200 years back, right? But the kudos to the strength of that equation that it is valid even now, right?
What does it state like?
No, it's not a law. It's
what are the factors in play in the Reynolds equation?
See, there are the most prominent ones, I would say, pertains to the load that acts, a lubricant, speed of operation, density, right?
Density of lubricant.
Correct.
Oh.
Right. So, and
that also has a play in lubrication.
Absolutely. Right. So, there is there's a lot of physical factors involved in play here, because it's a physical phenomenon, right? So, most of the regular physical factors such as viscosity and forces in play and density, speed of operation, right? Now all this is like part of that equation. Reynolds equation primarily says that the pressure that gets built up within the fluid film. See, you have two
moving parts
moving surfaces and a fluid film, right? Now, under load, the pressure that gets developed within the fluid film should be sufficient enough to withstand the load, right? So, what Reynolds equation gives you is, when solved, it will give you the pressure distribution, okay, across the surface. See, if you have a circular a bearing, and if I open it up and keep it in a two-dimensional sheet, right, at various points, what is the pressure, right? So, solution to the Reynolds equation will give me the pressure distribution across the fluid film.
Is it uniform or is it unequal?
No, it is unequal. Okay, at a certain angle, there is called as attitude angle. At a certain angle, you will have the point where the fluid film is the smallest. Okay, so that region, right? That region is where you have maximum fluid pressure as well.
Okay,
right? And see, we are talking about RPM that is 1500. RPM and more, right? Therefore, on the other side, opposite to the side of maximum fluid pressure, you will have vacuum pressures. Right. So there is this. Now, when you have a bearing here and you have a shaft, and the shaft is turning, right? Now, when it is rotating, there will be a climbing action. Right, that is, this shaft tends to climb over the surface of the bearing, right? And that movement creates a suction and it draws lubricant underneath, right? So this is it's like when you are driving on a road on a rainy day and you are taking a swirl, right? The water that is present in the road tends to get sucked inside, under the wheel. Right, because of which a vehicle can slip, right? So that similar action happens here, right? So that is how lubricant gets sucked into the maximum force region, right? And this is the lubrication, hydrodynamic lubrication. Hence the term hydrodynamic, right? So this phenomenon is described in Reynolds equation. Right? It actually it explains the science behind how the lubricant gets sucked inside. How does the pressure grow? How does the pressure vary with attitude angle? Right? All these, this physical phenomenon is clearly described using this Reynolds equation. So if you are a fan of mathematics, I suggest that you look at this equation. It's a marvel.
I'll try to go through it after the podcast.
Absolutely. It's just one equation, developed 200 years back, which is still relevant. It's still relevant.
Engineers still use it.
Yeah, absolutely. It is the basis.
What he was working on, like what moving parts he was testing? Did he have cylinder and
general bearings?
General bearings, okay.
General bearings, because general bearings is as old as any rotary system, right? So it was, even I spoke about the chariot wheels. You have a spindle, right? And that spindle and your wheel, there should be a gap, and that gap should be lubricated. So people knew this. So how can they increase the efficiency, right? Now what is happening is people are playing around with two things. Number one, that geometry of the bearing. They started playing around with it. Can I design the geometry of the bearing such that lubrication becomes more efficient? And can more load be taken without getting into surface contact? Journal bearing, the shape of the bearing can be modified. People started working on Lobo bearings. Right, and then people also thought of having something called as adjustable pad bearings. Instead of having a completely, circular sleeve, people started breaking into, segments, and individual segment can also be moved at an angle. See, you have the shaft in between. Instead of having a solid circular sleeve, you break the sleeve into multiple pads. Right, and that individual pad, depending upon the friction, can either go out or in. So you are making sure that oil film will always be there.
So you're reducing the area by cutting out minimizing the size.
You're adjusting the fluid film thickness. Right, so that way you are promoting the amount of load which the bearing can take.
Interesting.
Right, so as I said, so people are playing around with the geometry of the bearing. At the same time, they are also working in developing newer lubricants as well, right? And then there is a field of study in which the materials, the tribological properties of materials are in focus, right? As I said, if the material surface can have that sacrificial layer, which can wear out, but that wear will not affect the operation. Right, because friction you can't avoid at the end of the day.
Don't you think friction is needed to move a car? In a sense, I'm not talking about the contact between a wheel and the road, where friction is needed.
Exactly, absolutely.
I'm
road
talking
grip,
about the gears, right?
Correct.
So they have to be in contact.
Absolutely.
To transfer energy from one to the other part.
Yes.
So the transfer happens because of friction, right?
Definitely.
If there was no friction, can there be energy transfer from one part to another?
There are. You can see in an hydraulic system or in a pneumatic system. Okay, there we can use fluids to transmit power from one point to another. Okay. So there are systems in which you don't need gears. There are other ways in which you can transmit and play around with forces. But you make a very valid point when you say that friction is essential as well. Right. So as I said, I gave you the example of manufacturing processes. Right. If you will go see a lathe. Right, how does now lathe, unless you get into material contact and then remove, the entire machining process is because of friction and wear. Right, so there is an entire industry that runs on friction and wear. Right, so friction by say is not bad.
Yeah, of course.
Right? But when you talk about durability, right, of systems which we design and operate, that is where friction needs to be handled with care.
Nice. Yeah. So any other law you are like intrigued or fan of or something other than Reynolds law in tribology that that is still really important for the field of tribology?
Colloidal stability is like something that I actually worked on, right? Because as I said, increasing the stability of nanoparticle suspension in lubrication, right? Again, that's a challenge which we are facing even now. It's not yet resolved as such, right? So what I tried to do was I studied the nanoparticles in its hydrophilic and hydrophobic nature, and then tried to narrow down on a surfactant, which when coated on individual nanoparticles will prevent them from coagulation, right? The issue of stability is because when nanoparticles come closer to each other, the surface to surface attraction is so high that it will immediately form agglomerates and then settle down. So optimizing surfactants, there are plenty of surfactants in the market. Okay, so we worked on optimizing them, selecting the right choice for TiO2, titanium dioxide nano particles.
Why exactly titanium?
See, TiO2, the use, there are multiple benefits. Number one is it is one of the most chemically stable additive that we can think of, right? Now, I don't want the additive to get into chemical action with the lubricants.
Right.
That will change the property of the lubricants itself, right? And it's actually safe. See, handling nanoparticles is always a problem, right? Because there is always this issue of getting into the human body. But with TiO2, the general published notion is that it is actually safe, right? So there are many benefits in using TiO2. So as I said, I had to find a surfactant which works well with TiO2, right? And my the challenge that I faced was, how do I numerically quantify stability, right? So how do I measure stability, right? So what we then decided to do was, when you have a solution or when you have a suspension, there is something known as the amount of nanoparticles remaining at the top surface, right? That is the supernatant is what we term them, right? So what I did is, from the top 5 mm length of this nanoparticle solutions, I used to take out samples and carry out a UV visible spectroscopy. Okay, and a UV visible spectroscopy will allow me to find out what is the percentage of supernatant nanoparticles present now in the surface. Now, if I keep it undisturbed, this value is going to go down, right? So I started measuring that, right? Now, we prepared 50, 60, 100 samples, right? And God willing, I don't know how, but there was one particular sample which remained stable for 86 days.
That you mean by colloidal stability?
Absolutely. Every other sample that I made, overnight it was almost 80% sedimented. But this one sample, we were quite surprised. We actually stumbled upon it. It was not a
serendipitous discovery.
Yeah, absolutely. It was not a deliberate choice by any means, right? But then we spent a lot of time studying it. That one sample, we did n number of studies on that, and we based on that sample, we derived a process and we published it. So it's a optimal process of stability for TiO2 based nanolubricant.
So what are the applications of tribology? Like where, as you said, much thing about automotive.
Correct.
So what are the other places where tribology, the applications of tribology is already in play?
Well, you see, there is no field from which tribology is exempt, right? Everywhere where there is relative motion, tribology will play will have an impact, right? Every field where there is friction involved, tribologists have got a role to play.
Let me phrase question different way then. Where are the tribologists employed?
Okay.
Like where society pays the tribologist to get the knowledge or get the consultation or something.
Yeah. See, lubricant industry, right? They like hire almost all petroleum industries, right? Be it Indian Oil Corporation and all those like industries who actually deal with oil, right? Because tribologists understand lubrication much better, and they are actually trained to understand and experiment on lubricant and study its tribological properties. They have got a role to play there. Right, and it is very closely associated with mechanical maintenance as well, right? Because plant maintenance, say for example, you have got a huge manufacturing plant, TVS motors, anywhere, right? So all these manufacturing plants needs to be maintained well. So tribology as a field is very closely linked with machine health monitoring. Okay, something called as asset management. Right. How do you study the reliability of a machine? Now, lubrication and the tribological aspects play a big role there. Right. So, plant maintenance is one area I am very sure tribologists have got a significant impact. Right. Manufacturing. Now, when you are manufacturing, as I said, the process of machining itself is through friction, right? So there is a lot of tribology at play there, right? So again, automotive, manufacturing, oil lubrication, and I actually spoke about plant maintenance, asset management. Right, all these are actually fields which is open for tribologists, and largely R&D. Okay.
How about condo manufacturers? Just kidding.
Yeah, it does.
Probably.
Lubricants.
Right. Interesting field of research. And prosthetics, right? Like joints, as you said.
Absolutely. Artificial joints that we insert into human body. Number one, your choice of material for this joints is extremely important. They should be compatible with the body fluids, right? So that is like something of like importance, right? And there the artificial lubricants cannot be used, right? So therefore there it is tribological properties of materials which are of more focus on, right? So which are the materials with which we can prepare these artificial joints and get it inserted into the body, right? So a lot of R&D and research is going on in this.
Yeah, application. Okay, let me look at other detail.
Sure, please.
Yeah, engine components. We have talked about it.
Absolutely.
Pistons, bearings, gates to reduce wear and improve efficiency. Brakes and clutches,
absolutely. The way a clutch like operates and brake operates is through surface contact itself, right? But there friction,
we need more friction.
There's no point in lubrication there, because we need efficient friction there,
right? So
for it to
even
function
increasing friction between the surfaces is also part of tribology. No,
tribology as such deals with negating friction.
Negating friction.
Exactly, but there are applications where friction is good, right? But tribologists are not much interested in that.
Okay. To increase friction.
Yeah, exactly.
Okay, then we have joint implants.
Joint implants, absolutely.
Tribology helps in designing artificial joints that mimic the natural movement and reduce wear over time.
Correct.
As well, dental applications. It is used in development of dental implants and restorative materials.
Yes.
You have mentioned HelioFit, manufacturing and machinery, bearing and gates, lubrication system.
Correct.
Then renewable energy, wind turbines.
Exactly.
Tribology is used to improve the performance and reliability of wind turbine components.
Every rotary system, every turbo machines, right? Everywhere all systems which involve rotary transmission of energy and power, they'll need some or the other form of journal bearings, right? And their lubrication is a must. So in the design of the bearing itself, we need to start thinking about how efficiently can you lubricate it, right? So bearing design is an important aspect of tribology, right? Design of roller bearings, journal bearings, hydrostatic bearings, right? So bearing design is an integral part of tribology. Now what's happening now is this field has been in play for so many years that journal bearings and ball bearings, roller bearings, for almost all load applications, it is well designed, right? So at the moment, for me, for an application, I just have to choose the right one. Okay, say for example, SKF bearings. SKF has got bearing solutions for all our needs, but I should be smart enough to decide which is the right solution for my application, right? And that knowledge comes from tribology.
Nice. So the fact that there are many bearings existing is because of tribology.
Absolutely. And you cannot use oil lubrication in say aircrafts.
Interesting. So what is used as a lubricant in aircraft?
You will normally go for ball bearings there, which can be lubricated by grease and so on. Because the issue with an aerodynamic bearing is that in case if there is oil starvation, imminent seizure, failure, you can't take that risk with an aerospace like industry, right? Because
Is it because they have operate in very high temperature? That's why you can't use oil, is it?
Yeah, that is a reason. But mostly oil starvation needs to be eliminated. God forbid any reason causes lack of oil flow. Your automobile seizes, you are on road, right? And if some seizure of that nature happens at an higher altitude, you're gone.
You go much higher.
Yeah. So that's the reason why most of the aerospace industries, they don't actually prefer journal bearings.
So they operate on grease.
Ball bearings, yeah.
Okay, ball bearings, so which is internally grease, right?
Correct.
And now, pretty curious about grease's component. I never thought what is grease made of.
Okay.
So what is the material structure, what is the composition of grease? Is there also a colloidal stability you were talking about? Does that play any role in the grease?
I'm not studied grease much, but from what I know, I will say that it is also a petroleum based product itself. Okay, but it's not a fluid, right? It's a should I say
colloidal mixture,
a semi-solid. Probably I would actually say that, with a lot more additives and chemicals that go into manufacturing them. Right? It doesn't flow, and it's actually used where the load is very high, but which is not subjected to very high speeds.
Right? So it can resist the amount of load
that can act. Speed does play a major role.
Okay, and also opposite to that, is there a limit to speed?
Yeah, of course. See, again, in an aerodynamic lubrication, as I said, there is complete separation of materials, right? And the entire force, the shear force, is taken care of or is supported by the pressure built inside the fluid film. Now, at extremely high RPM, that fluid film can break down. Right? And the moment that fluid film breaks down, that's the end of lubrication there. Right. So speed, there is an upper limit to speed for every application.
And that's why you mentioned F1 is because of advancement in tribology.
Absolutely.
Because you can figure out.
As the load and speed needs, okay, load and speed are two demands based on which tribologists work. Right? So the load speed demand is the factors based on which you go for a proper selection of bearing, proper choice of lubricant.
And another application, advanced coatings, which you worked on, nanotribology helps in creating coating that reduce friction and wear at the nanoscale. Aerospace, as you mentioned just now, spacecraft components. Tribology is critical in ensuring reliability and longevity of components used in spacecraft and satellites.
Correct.
Interesting.
Correct.
Aviation.
Absolutely. Basically, those applications focus more on selecting the right material, right? Because their lubrication is not a sustainable solution there, right? There you should, the material by nature, because of its surface properties, should be tribologically useful. Right? Because you can't think of having lubricant flow at very less gravity solution, right? Because you will not, it will not work out.
Gravity in play, right?
Correct. So fluids are not a solution there. It could not be a solution. So you need to look at solid lubricants as well. Graphite.
Right.
Okay, graphite is a solid lubricant. See, graphite doesn't resist shear. I mean, it's actually very limited resistance to shear force, right? So if you are using graphite as a lubricant, right, friction is there, but at operational load and speed, it can work. So there is a lot of research happening on solid lubricants as well.
Right. Doesn't it break when the load is lot?
It does. No, you're not talking about cubes of, as I said.
Right. Sheets of.
The area of lubricant film is very less. Right. So you're actually talking about very limited amount there.
I just imagine I'm breaking the pencil lid.
No.
Because load is more.
Exactly. And no, we actually want it to break. See, we want that shear to happen.
Oh, okay.
Right, we actually want it. See, if your graphite holds up, and if it will resist movement, then it is increasing friction.
Right.
So the benefit of graphite is that it shears off like easily.
So where is graphite used as a lubricant? Which places?
You just now spoke about everywhere where fluids can't be used.
Where, like example?
Say for example in industries where oil is bad. Say for example, pharmaceuticals maybe, okay, where in case if oil gets mixed up with the product, it will be an issue, right? So food industry, right? So probably those areas where lubricants, fluid lubricants is not mandated. We could think of having solid lubricants as well.
Nice. So one more, it's used in sports equipment.
Yeah.
It is used to improve the performance and durability of sport equipment like skis, skateboards and bicycles. Interesting.
Absolutely. Bicycles, as we know, there's a lot of, it actually works on grease, right? Because we've got chains in play.
Shimano.
Because lubricant won't stay there because it's open surface. Right, so you need to have grease because grease can hold on to the metal surface of the chains and then do the. That's another area where solid lubricants becomes more important. When you see fluids can only be applied where the system there is a reservoir which can hold the fluid lubricant. Otherwise, it will just flow off, isn't it?
Nice. So, what are the new ideas? Like you mentioned about nanoparticles used in...
Correct.
That was one idea we
these days
explored.
Correct, absolutely. I was reading that there is a lot of need for green lubrication. Lubricants by nature has got a lot of chemicals in it. Okay, there used to be a lot of use of sulfur, right? And the materials that goes into formulation of lubricants can contribute to greenhouse emissions as well, right? So it is important to build or formulate lubricants which are sustainable, right? The paper that I was reading about tends to make use of calcium carbonate as a additive, right? So that is one area of tribology in which there is a lot of work happening. The reason why my PhD student is working on an organic lubricant, biolubricant, is because of that, right? To make sure that the lubricant is sustainable. So that is one field of study.
So is there a place where huge quantity of lubricant is needed? Like lubricants are used in trace amounts, right? Like not too much. Like
no, if you look at a manufacturing plant or where there are heavy machines in play, right? You will need to have good amount. See, there is applications which involves submerged bearings, right? That is, the lubrication is so important that this rotary system bearing, this entire system is immersed in a container full of oil. Right?
Okay.
So to always make sure that there is a lubricant. Right. So that is one area. So there are, depending upon the application, depending upon the area of application, the need for lubricants will vary.
Okay. What is apart from green tribology? What are the other areas?
Yeah, other areas of interest I would say is, of course, nano tribology. It is opening up spheres, right? Where we are, as you said, we are looking at the relative motion at the atomic level. Right. So how can we eliminate or try to reduce friction at that scale? Is again something which is been under study for more than 2 decades.
And design custom surfaces.
Correct. Absolutely. Right. Yeah. Absolutely. So that is studying tribology at the nanoscale will open up a lot of avenues to bringing down friction. Is what I feel.
Can lead to better medical equipment.
Absolutely. Then AI and ML, artificial intelligence and machine learning is these days applied a lot more in studying machines' health, right?
Okay.
Predicting failure.
You mean they're taking data from machines?
Exactly.
On the performance?
Absolutely. You will have n number of sensors mounted on those machines which are involved in a manufacturing process, right? It will constantly measure the vibrations,
motion.
Correct. Temperature, the pressure, right? Noise levels. These sensors will record these data, and you are able to predict failure. So you are able to, you will be in a position to understand the consumption of lubricants much better. And
how much lubricant is needed?
Is there a possibility of oil starvation? When do you need to replenish it? Right? That is one thing. And lubricant has also got this additional benefit of carrying away, parts which indicate how well your because there is a surface contact happening. Lubricant flows through it, right? So whatever little particles that gets formed there is taken away by this oil, right? So you study that oil, and that oil and that oil analysis will give you
separate
indication.
Set of data.
right? About is there wear happening? How much amount of wear is
Particles
happening?
from the
Exactly.
moving parts are present in the oil.
Exactly. So that will give you a better picture into the health of the instrument as such, right? So
Interesting.
artificial intelligence is used heavily now. In fact, yesterday I began a course for my students.
Oh,
It's
okay.
like
What's
brand
it
new
named?
course. It's AI for mechanical engineers.
Okay.
We actually felt the need for that. Right?
Where do you think it can be, where AI can be put in mechanical
Everywhere. See, there is this field of generative design, right? I need to optimize the weight and strength, right? Normally we do manual calculations, and we use software such as ANSYS to analyze the weight distribution so that I can bring it down. Now that AI is there, it will augment my ability, right? It will give me options. It will engage with me in my design process, and like make sure that the component that I design has got minimum weight and maximum stiffness, right? So that's like a one field. Next, as I said, predictive maintenance, right? When is a machine expected to fail, right? When do I need to replace the bearings? Okay, so that sort of maintenance activities and scheduling the maintenance activities can be more efficiently done now. Okay, so that is an area. And smart manufacturing, right? Additive manufacturing, right? And fault detection in the parts that I make. Say, for example, if I'm manufacturing 1 lakh bolts and nuts in my plant, it's not feasible for me to do a quality check of every part, right? But then your AI through image analysis. Now, if every part is undergoing there is a camera that is recording it. Based on these images, the computer vision software can actually identify micro cracks.
Too much processing.
Yeah, crazy it is. I mean, the amount of applications that you see and think of, the possibility is actually huge. So these days, I don't think it is safe for a mechanical engineer to not have sufficient knowledge about deep learning algorithms, right? It is very soon going to be an integral part of our work. Right, so we have
it's
made
just
an
like
early
a calculator, adding calculator to work. Like these AI tools are nothing but calculators.
Absolutely, at the most basic sense, it is computations, right? It is algorithms.
Yeah, something they call predictive computing.
Absolutely,
like it can't give you certain answers, but it can give you predictable.
It will give you probability.
Yeah.
And if the probability is around, say, 60% of more, we could consider that as a good prediction, right?
Nice. So there is something called high temperature tribology.
Yeah.
So what do you mean by high temperature? You meant the jet engines?
Elevated temperatures where there is combustion involved.
What is high temperature in tribology? What is the range we are looking for?
The normal bearings and lubricants that we use barely crosses around 70 degree Celsius. Anything above that, your lubricant loses its viscosity entirely, right? So it doesn't satisfy its purpose. Imagine dealing with 300 degree Celsius, 400 degrees Celsius and more. Your lubricant will vaporize. Right. So how do we deal with that? Okay. So there you need to focus on the tribological properties of the materials itself. You cannot have a medium there. Right. So the materials that we choose and the properties of the materials itself will have to take care of friction there.
Even turbines deal with
turbines
the friction
as well. Yeah, of course.
Then they will operate in very high temperature.
Yeah. See, depends on the system where or the space where the temperature is high. See, normally even if you have a 3000 RPM shaft and a bearing, okay, the temperature can be brought down. see, the lubricant itself takes away the heat. Lubricant can also act as a coolant as well.
Oh, interesting.
Yeah, so that's the dual benefit there, right? So turbines is fine. Turbines are all sorted out. Okay, that part of it, your normal lubricants are enough. I'm actually talking about scenarios where the temperature goes above 150, 200 degree Celsius. So there, your typical petroleum-based, your oil-based lubricant won't work, right? So that's what they actually speak about.
Okay.
It's an ongoing research.
And there's something called self-lubricating materials. So you have any takeaway on self-lubricate? Have you done any,
No, I have not done any work on that. But there are many people who actually believe that tribologists will become redundant in many years, right? Because there is no need for lubrication. The material that we use to design and manufacture itself will be self-lubricated, right? But that's not happening in the near future, is what I would feel.
So what is the idea of self-lubrication?
Idea is that the material itself is we actually spoke about how graphite is a sacrificial surface that we actually give in between. What if the material with which you make the two surfaces
are made of graphites?
Are made of, I'm not saying graphite, but of substances which are
self-lubricative, just like graphite.
Exactly. Right. There is something called as smart materials.
Okay.
Right.
Materials, right?
Yeah. Now, smart materials, how they behave is depending upon the ambience, depending upon the environment in which it is operating, it will behave in different ways. Honeycomb structure, right? There are plenty of material structure and material science that are in play. Okay, which is what we call as smart, right? I mean, they actually tend to remember the shape, right? So again, there's a lot of research that needs to happen, and self-lubrication, long way to go. Yeah.
I think we have done, I've got a lot
Thank
of idea
so much.
on
Thank you so much, Clinton.
tribology. My biggest takeaway is friction, wear, and lubrication.
Right.
And factors governing the lubrication.
Correct.
And I would remember, I'll never forget Reynolds law.
Correct. Reynolds equation.
Reynolds equation.
Yeah.
The future looks interesting.
Absolutely.
The microscopic factors involved in tribology.
Correct.
The
nanotech that goes into play.
Nanotech, and even that surface undulations.
Correct.
Now how they play in the macroscopic friction.
Absolutely.
It's quite great.
Correct.
Maybe I think there could be. There's already a term. Maybe quantum friction as we go more deep and deep.
Absolutely. It will. These are phenomenon that we are not sure of now, right?
Right.
When
Let me check though. You please continue.
No, when you are talking about, you raised a very interesting point there. What happens to friction at the quantum realm, right? Quantum realm, you are not even sure where an electron is.
Yes.
Right, then
it's vibrating.
Yeah. The all known knowledge of tribology goes out of the window there, right? So yes,
new avenue for tribology.
Absolutely, quantum tribology. You coined it first, Clinton.
What is quantum friction? Let me see. Oh, there is a term, quantum friction.
Okay.
Quantum friction refers to energy dissipation that occurs in quantum mechanical system due to interaction between quantum particles or fields.
Right.
So there is a friction between fields. Interesting. Unlike classical friction, which arises from macroscopic interaction between surfaces, quantum friction occurs at the microscopic level and is governed by quantum mechanical principles.
I should say even at the nano level.
Nano level, right?
Nano level, yeah.
So aspects are quantum fluctuations, Casimir effect, atomic scale interaction, superconductors and superconductors.
So superconductors.
So the application of quantum tribology would be arisal of superconductors.
Correct.
100% transfer of heat energy, right?
Absolutely. Yeah.
Oh, even electricity loss is because of friction in the atomic level.
Exactly. So you can see how it is all interconnected. It's like something as simple as two atoms rubbing against each other, and the energy that it produces, the heat that it produces. At that scale, it is huge, right? So
interesting.
Cool areas to study into.
Yes. So before I end up the podcast, before we wind up the conversation, you have any advice for those who are really thinking of taking up tribology as a career?
Absolutely. My message for those of your viewers who are interested in pursuing research and R&D, if you have interest towards mathematics and experimental science, it's a field which will give you a lot of happiness. I mean, a lot of fulfillment, right? Because you get to work on some wonderful theoretical solutions. Like you can rake your mind on math, right? Develop nonlinear equations, solve them, use MATLAB. Crazy it is. I mean, it's actually very, very interesting. At the same time, whatever you analyze, you could easily validate it. Because the experimental side of it, the journal bearing rig that we design, the foundation is solid, right? So there is scope for lots of research gaps to be addressed. There's like plenty of work to be done. So it's an open field, growing field. Anybody interested in math and physics, it's a great field to it. I would also say that there are a lot of mathematicians doing their PhD in hydrodynamic lubrication.
Interesting.
They don't know much about the physical aspect about it. But as I said,
they're strong in theoretical.
They're fascinated by the Reynolds equation.
Nice.
They actually see that equation and they go crazy.
Reynolds equation seduce them into hydrodynamics.
Absolutely. The mathematics is so beautiful that,
fluid dynamics is in play. Friction between not just the two moving parts, but also the layers of the lubricants is in play, right?
Oh, yes, absolutely.
Amazing.
That's where the friction is.
It's like series-wise and number. I'm thinking now.
Correct. And fluid flow is in place, right? Fluid dynamics is in place, right? So it's multidisciplinary. Everything is there, So
multidisciplinary, multi-layer,
it's quite an interesting field to do research.
Yeah, thanks a lot.
Thank you so much, Clinton. I enjoyed it. I don't know about you, but I enjoyed it.